Hi everyone, welcome to the second section of chapter 11. We're going to deal with probability in this section. And we're going to start off by talking about experimental probability. So the experimental probability is different than theoretical probability. It's not saying, okay, if I roll a number cube, the probability of getting a 3 is 1 out of 6. That's a theoretical probability. With an experimental probability, you would actually roll a number cube like at least 20 or 50 times and keep track of how many times you rolled a 3 and then use that ratio, your number of 3s out of your total number of rolls, and that would give you your experimental probability. So experimental probabilities come from actual trials and results that you get. For instance, here's one. You go in a parking lot at a school, and let's say in the teacher's parking lot, out of the 60 cars that are in teacher's parking lot at the school, 15 of them are pickup trucks. So what's the experimental probability that a vehicle in the lot is a pickup truck? So you just counted them, and 15 out of 60 were pickup trucks. So based on that experimental probability, the probability of a car at random being a pickup truck is 15 out of 60, or 1 out of 4, or 25%, okay, or 0.25. You can do probability as fractions, as percents, or as decimals. That's what experimental probability, that's what it means. Let's say a softball player. Here's the got it question if you understand how this works. A softball player has got a hit in 20 of her last 50 times at bat. So the last 50 times she's gone up to bat, she's gotten a hit 20 of those times. So she's gotten a hit 20 out of her 50 at bats. What's the experimental probability that the next time she goes up to bat, she's going to get a hit, and it's going to be a hit? Did you figure it out? Figure it out before I give you the answer. Okay. It is 2 over 5, or 0.4, or 40%. It's a 40% probability that she will get a hit on her next at-bat. That's how experimental probability works. Sometimes we want to look at experimental probability, but it is not reasonable or even possible to run an actual experiment or test, or we don't have the records. So then you could create something called a simulation to kind of simulate some random occurrence and then see how much time would get out of this simulation. And we're gonna use our calculator's help to do this. Here's an example of what I'm talking about. Let's say that there's a multiple choice test, and you have all of them have 4 possibilities. A, B, C, or D, whatever. Only one of them is the correct answer, and there are 10 questions on this test. How can you simulate if you guessing all the answers? Because it would be totally random, right? So you would want to come up with a random answer for each one. So how you could simulate a random guesses out of the 4 possibilities, you can use your calculator. It can actually generate randomly produced numbers, and they would be random. And then you can use that to say, okay, well, what's the probability that you're going to pass the test by getting at least 6 out of the 10 correct? And you can run a simulation using your calculator to figure that out. By the way, it's not very high, so don't guess, study. All right, in any case, you would have to pass, you can get 60%, right? 6 out of 10 right. So the first thing we need to do is generate some random numbers. The calculator says, or I'm sorry, your textbook says that you can use this random integers, generate random integers, and then it shows parentheses 1, 4, 10. And what this means is you're generating numbers 1 through 4, and you're doing that 10 times. Some calculators can do that, and then what you will have is a series of 10 numbers that are 1 through 4 when you do that in your calculator. Okay, this one will generate random numbers, but it will not generate 10 at a time. But it will generate 1 at a time. So I can go into, with my calculator, I can do random integers as well, but I can only do this. So I want it to randomly generate integers between 1 to 4. And then I just keep hitting the enter button for each number. So I would have to hit the enter 10 times to see what my randomly generated guesses are for my 10 questions on my test. Now before you run this, you have to decide, okay, which digit's going to be the correct answer? 1, 2, 3, or 4. You pick one of them. You say just randomly. In fact, if you want, you can randomly generate one number, and that can be what your correct one is. And you can say, okay, that's my, let's say it ends up being number 1. We're going to say number 1 is going to be our correct. So you randomly generate 10 numbers, and you see how many times you got a number 1. And you write that down. And you do it again. You should do this at least 20 times. So if you can't do this and have to do this, you're going to be hitting enter a lot and writing down to keep track what you got, or hits or misses or whatever. There's an example in your book of how they did this. And then they went through and they checked how many of them at least had 6 ones out of those 10 numbers. Not a whole lot. In fact, when they did it, they took the test 20 times, and out of those 20 times, only one of them passed. So then they realized, okay, only one of those group of 10 numbers had at least 6 ones in it. So 1 out of the 20 was a pass, and that's like, what, 5%? Yeah, that's only a 5% chance that you're going to pass just randomly guessing multiple choice answers. But that's how you could run a simulation and use your calculator. Experiment with that. Let me show you. It's usually in probability. There's a probability button often. So in mine, in this calculator here, if I hit probability, I see PRB, and then I see RAND. So I'm going my arrow over to RAND, which is random, and then I can see RAND, and then RAND int like this with this, and so now I can do that. Enter 1, 4. Usually the comma might be a shift key above the period, but there is a comma somewhere. Find the comma to separate these like an ordered pair. Close the parentheses and then hit enter, and you'll get those randomly generated numbers. So this one is all about experimenting with your calculator and seeing if you can do that. The guided question is to do it in randomly generated simulation. What if you could pass with 5 out of 10 correct? What's the probability that you would pass running a simulation for that? I can't tell you what the right answer would be because your trial might be different than somebody else's trial. That's the whole point. These are randomly generated. I will tell you that the more you do it, the closer you'll get to what the actual theoretical probability would be. But you have to run a lot of tests to get close to the theoretical probability. But that's as much as I can tell you about how to generate random numbers and come up with a simulation. And you can do it for all kinds of different things. This is one example. If you cannot figure it out on your calculator, by all means, Google, how do I generate random numbers using my TI or my Casio or whatever calculator you have? How do I generate random numbers using this? And you will get all kinds of stuff on the internet that'll tell you how you can do that with your particular calculator. So have fun with that and explore. And now we're going to leave experimental probability, and let's talk about theoretical probability. So theoretical probability has kind of like a sample space. These are all the possibilities that can happen, that we can expect is our sample space. And we can come up with a theoretical probability if anything within that sample space is like equally likely to happen. For instance, flipping a coin, could be heads or tails. Or rolling a number cube, it could equally be a 1 or a 6. That's when you can start to generate theoretical probabilities of something happening. The probability, so when we want to talk about the probability of an event occurring, so we would designate it this way. This is the probability of A, or the probability of this desired outcome. It would be equal to what's the desired outcome out of all the possible outcomes. For instance, if I roll a number cube, what's the theoretical probability that I will roll a 1? Well, the probability is the ratio of the numbers of 1, which is 1, out of the total number possible. It's a 1 out of 6. That's my probability of that occurring. So, unfortunately, we're not going to be doing such simple things as, oh, 1 out of 6, I can do that. No, we're in Algebra 2, so expect it's going to be a lot harder than that. All right, let's look at, let's start with something that's simple, and then let's move on. What is the theoretical probability of getting a 5 on one roll of a standard number cube? And you guys can do that. There's how many 5s are there? There's only one 5, and there's 6 possible numbers. So it's 1 out of 6, and you can divide 1 by 6. So you could say this is the probability of getting a 5 is 1 out of 6. See how we've designated that? Probability of getting a 5 is 1 out of 6. What is the probability of a sum, S-U-M, a sum of 5 on one roll of 2 standard number cubes? This is trickier because you have to know how many different possibilities there are when you roll 2 cubes. And it's not like 2 through 12. Because you have 2 different cubes, and so you have 6 possibilities on each cube. So you have 6 times 6. There are 36 different rolls that you can get with these cubes, because you could roll a 1 and a 4 and a 4 and a 1. Do you see what I mean? So there are 36 possibilities, and to roll a 5, you have 1 and 4 and 4 and 1 and 2 and 3 and 3 and 2. So you have 4 out of the 36 of getting a sum, S-U-M, a sum of 5 on your roll. So the probability then of having a sum of 5 is 1 out of 9. And then you can leave it like that if you want. Or you can go 1 divided by 9 and give me the decimal, or you can do a percentage, but fraction works too. So that's that. Okay, your turn. What is the probability, the theoretical probability, of getting a sum that is an odd number on one roll of 2 standard number cubes? So I'm rolling 2 cubes. What's the theoretical probability that my roll will be odd? Okay? Figure that out. Half and half, 50%. The answer is 1 to 2. It's 50%. Okay, now the rubber meets the road. We learned about permutations and combinations. We can actually use permutations and combinations in probability, in figuring out probability. Let's say you guys are bored and you decide to get your penny jar and you decide to play a card game with your pennies or whatever. Heaven forbid. But let's say you decide to do that. Let's say you're dealing 5 card hands. What is the theoretical probability of being dealt exactly 2 7s in a 5-card hand from a standard 52-card deck? Oh boy, exactly 2 7s in a 5-card hand out of a 52-card deck. All right, So remember to figure out a probability. It's what you're looking for is on top out of all the possibilities, which is down below. So the possibilities are all the hand combinations that you can get out of those 52 cards. Deck of card has 52 cards. So it's all the combination, and if this is, order doesn't matter. So this is definitely combination, not permutations. We have 52 cards, and we have groups of 5 out of those 52. So all the possible 5 cards we can be dealt from 52, that's the whole possibility realm, that's our denominator. Now, we want to know exactly 2 7s. So that means 2 of our cards are going to be 7s, and 3 of the cards are going to be something else. So for the numerator, we're going to represent the 2 7s this way. It's the combination of, and there are 4 7s in a deck, right? Okay, so we need 2 out of those 4 7s times, and then the other 3 cards have to come from the other 48. That's how you do your numerator. This 2 of the 7s, 2 out of the 4, and 3 out of the other 48 cards are what your hand makes. So you take this times this, divided by that, and you will get a percentage. So try that with your calculator. And they did this for us in our book, and you get 0.003999999, or about 4%. Okay, I want you to try that with your calculator and see if you get that percentage. And if you do, good for you. Remember how to find the combinations using your calculator. Okay, good. Let me give you one to do. What is the theoretical probability of being dealt all 4 7s in a 5-card hand? All 4 7s in a 5-card hand. Okay, here's how we did the first one. How are you going to change this to represent all 4 7s? And then what is this final answer going to be? Pause it, figure it out, and then I'll show you what the answer is, okay? Okay, if you want all 4 7s, this should be a 4, that should be a 1, and this doesn't change. When you multiply that out, obviously you're going to get a much smaller number. It is 0.1234 zeros, followed by 1.8184689. Okay, or this is 0.00185%. That is a very, very small likelihood to get all 4 7s. Goodness gracious. How did you do? Is that what you got? If you did, good for you. And I hope that this made sense on how we set that up. Yeah. All right, we can also find probability with geometry. Geometric probability is usually is defined in areas or segments of lines or things like this. For instance, a batter has a batting window, a batter's box, not a pitching zone, the strike zone. That's what I'm looking for. Ha! Mrs. K got it. A strike zone that is 17 by, 17 by 22. Here's the strike zone in front of the batter. Okay, so what's the probability that a baseball thrown at random within the strike zone, it's in the strike zone, what's the probability that it will be a high inside strike? This is one of the hardest pitches to hit. And this high inside strike zone is 4 by 6. Okay, so how would you find the probability that it's a high inside strike? So what you do is you find the area that's desired, which is 4 times 6. 4 times 6, that's what we're looking for, out of the entire strike zone, which is 17 times 22. So it's 24 over whatever 17 times 22 is. and then you divide that and you get about 6.4%. 0.064 is about what that is. Okay, so about 6.4% that it'll be that high inside strike that pitcher is looking for. Not the batter. The batter doesn't want it. Those are hard to hit. Suppose, okay, your turn. Suppose a different batter comes up, a little smaller batter. His strike zone is 15 by 20. And the high inside strike zone for this one is 3 by 5. Okay? Find the probability that a baseball thrown at random within the strike zone will be a high inside strike. Okay, find that. Pause it if you need to, and check back and I'll give you the answer. You should have got 5%. It's 3 times 5 divided by 15 times 20. All right? Okay, so that's probability. And generating, we talked about quite a bit, experimental probability and generating random integers, and theoretical probability only in more complicated things like rolling 2 die combinations or even cards. Cards can be so confusing. So work with that the best you can. That is 11.2, and I will see you guys next time. Bye.